So let's consider this position time graph. We've got a particle, maybe it's a car, who knows what it is, whose position starts out at 0, at t equals 0, and position is maybe around 10 when t equals 1, and whose position is around 40 when t equals 2, etc. It's following this position time function, this parabola. Clearly it starts off kind of slow. During the first hour, it's only traveling 10 miles down the road. But by the time it travels that last hour from position 3 to position 4, it travels from 90 to 160. So that's a much farther distance in that hour. So the last hour this car is driving or this particle is moving, it's moving much faster. So this thing must be speeding up. And we can kind of see that because the slope, which would represent the velocity of the position function, the slope is 0, and then it gets steeper and steeper and steeper. The steeper the slope gets, the faster the velocity is, the faster the particle is moving. So first question we're going to ask is, what is the particle's average velocity over 0 to 4? Well, the velocity is the change in position, so the average velocity will be the change in position divided by the change in time over the interval 0 to 4. So the change in position would be s of 4 minus s of 0 over 4 minus 0. We're just finding this slope, right, between two different points, 0 comma s of 0 and 4 comma s of 4. We're finding the slope of this dotted line. So s of 4 is 160 miles. S of 0 is 0 miles. So we've got a number of miles in the numerator, and we've got 4 minus 0. Time is measured in hours in this problem. So we've got 160 divided by 4, 40 miles per hour. That would be your average velocity over that interval of time. So one question we could ask is there a time during this interval from 0 to 4 where the particle is moving at 40 miles per hour, right? It starts out at 0 miles per hour. It ends up at, well, I'll let you guys think about that. The slope here, you should be able to figure out the slope at this point. You should probably be able to figure out that that's 80 miles an hour. So the question is there a place somewhere between t equals 0 and t equals 4 where the instantaneous velocity is equal to 40 miles per hour? And the question is when, if so. So you would say, well, we know the velocity function, right? The velocity function is the derivative of the position function with respect to time. So we bring that 2 out front. 2 times 10 is 20. The t is now raised to the first power. That's our velocity function. And our question is, does this thing ever equal 40? And, of course, the answer is yes. It equals 40 when t equals 2. When t equals 2 hours, velocity equals 40 miles per hour, which is equal to the average rate of change from 0 to 4. Notice not only that the velocity, the instantaneous velocity is equal to the average velocity, but also the time when the instantaneous velocity is equal to the average velocity is between the beginning t value of 0 and the ending t value of 4. Not very surprising. And in fact, you might say, well, it happens exactly in between. Well, that happens because perhaps this is a parabola. That way the derivative is linear. But that's not always going to happen. So just don't assume that it's always the midpoint. All right. But I guess my next question would be, is this always going to be true? Could we come up with a position function, a position time function, that we could find the average rate of change, right? We could find the slope between the two endpoints, but there is no place in between the two endpoints where the slope of that curve is equal to the slope of the secant line. In other words, the average rate of change never equals the instantaneous rate of change. Okay, so I'll let you guys think about that, and maybe you can come up with your own examples. And if you like, you can start at the same point at 0, 0 and end at the same point of 4, 160. So we still have the same average rate of change, but see if you can somehow come up with a position time graph where there is never a slope of 40 between these 2 points. And I bet you guys could come up with something. So give it a thought. All right. So here is the concept that we're discovering here. It's the mean value theorem. The mean value theorem, the last of the value theorems, right? We've got the intermediate value theorem and the extreme value theorem. Now we've got the mean value theorem. Mean meaning average. The mean value theorem says that if we find that average rate of change from one endpoint to another, that we will be able to find some point along the curve such that its slope on that point is equal to the slope of the secant line. So maybe that point is round about right there. And not only that, but that point's going to have an input value, an x value, somewhere between a and b. Okay, normally we call that C. Calculus is an interesting subject because we often put C in between A and B for whatever reason. So at any rate, we know that this is going to happen provided 2 important prerequisites. Okay, those 2 important prerequisites are continuity and differentiability. The function has to be continuous over the closed interval, and it has to be differentiable over the open interval. So you can go back to what I was asking about over here and take a look at the examples that you came up with. And probably if you were able to come up with an example that where the a-rock was not equal to the i-rock, then it was because either your function was not continuous or your function was not differentiable. Good. So if that's true, if we have a function that is continuous over the closed interval and differentiable over the open interval, then we will be able to find, we are guaranteed to be able to, we guarantee that there exists a point, at least one point C between A and B, such that f prime of C equals, well, what? Well, let's see what we can figure out here. This is the derivative, right? So that's the instantaneous rate of change. The other rate of change we've been talking about is the average rate of change. And how do you find the average rate of change? Remember, that's just the slope, right? This is the point B comma f of B. This is the point A comma f of A. And if we find the slope of that secant line, that's going to be f of B minus f of A, the change in your y value, divided by B minus A. That's the average rate of change formula. You learned it in Algebra 1. It's the slope formula. What the mean value theorem says is there will always be some value C between A and B such that that equation is true, provided that these 2 prerequisites are met. The function is continuous over the closed interval and differentiable over the open interval. These are important requirements to know. There are 2 of them. Both of them must be met. Sometimes you'll be asked not, does it meet the mean value theorem, but why does this function meet the mean value theorem, or why does it not meet the mean value theorem? And you will be required to identify its continuity / differentiability on the interval.